Imagine discovering a billion-dollar resource underground. Exciting, right? Now imagine losing half its value because of poor planning. That is exactly why field development planning exists. This course is about turning a discovery into a profitable, safe, and operable asset. Whether it's a desert oil field, a deepwater development, or a gas field offshore Malaysia, the challenge is the same. Make the right decisions before spending billions. Throughout this module, we'll explore the industry's dominant decision-making framework, the stage gate process. By the end, you'll understand how world-class operators reduce uncertainty, control risk, and maximize value long before the first barrel is produced. Let's start with a common misconception. When people hear field development plan, they often think of a reservoir study or an engineering design package. In reality, it is neither of those on its own. An FDP is the integrated plan that converts a hydrocarbon discovery into a producing asset. It answers 4 fundamental questions. What do we have in the ground? How are we going to recover it? How will we process and sell it? And will doing so create sufficient value? Notice how many disciplines are involved in answering those questions. Geoscientists define the resource. Reservoir engineers forecast performance. Wells teams determine how to access the reservoir. Facilities engineers design the production system. Commercial teams evaluate economics. HSE ensures the development can be executed responsibly. This is why the FDP becomes the integration point for the entire asset. I often ask teams where FDPs typically fail. The answer is rarely because one discipline made a catastrophic mistake. More often, the failure occurs at the interfaces between disciplines, where assumptions don't align. That's why integration is the defining characteristic of an FDP. One of the most important principles in field development planning is that project outcomes are largely determined long before major spending begins. The figures shown here illustrate that relationship. First, benchmarking studies consistently show a significant difference in cost overrun performance between poorly defined projects and well-defined projects at FID. The gap can be on the order of 2 to 3 times. The implication is clear. Definition quality matters. Second, approximately 60 to 80% of a project's ultimate value is effectively set during front-end planning. By the time major construction starts, the most important decisions regarding concept selection, facility size, well count, development strategy, and execution approach have already been made. Third, the amount spent on front-end planning is typically very small relative to total project capital expenditure, often around 1 to 3%. Yet that small investment influences the performance of the remaining 97 to 99% of project spending. This is why experienced project organizations take front-end loading seriously. The objective is not to produce more studies. The objective is to reduce uncertainty before large capital commitments are made. As highlighted in the instructor note, these values should be viewed as industry order of magnitude findings rather than project-specific numbers. The key message is that rigorous front-end planning is inexpensive compared with the cost of correcting mistakes during execution. So if there is one takeaway from this slide, it is this. A small investment in project definition has a disproportionate impact on project value and project performance. Before we go deeper into the stage gate process, it is important to understand where the FDP sits within the overall project lifecycle. Every field development starts with explore and appraise. The objective here is to confirm the discovery, understand the reservoir, and estimate the resources that could potentially be recovered. The project then moves into select. At this stage, the team develops multiple concepts and evaluates them against technical, commercial, and operational criteria to identify a preferred development option. Once a preferred concept has been identified, the project enters define. The focus here is to mature that concept until it is sufficiently detailed and robust to support a sanction decision. After approval comes execute, where detailed engineering, procurement, construction, and drilling activities take place. The asset then enters operate, often for decades, during which production, surveillance, and reservoir management activities are carried out. Finally, the life cycle ends with decommissioning, where facilities are removed, wells are permanently plugged, and the site is restored. One important point is that different companies may use different terminology, but the life cycle itself is largely universal. The FDP is developed and refined primarily during the select and define phases and becomes the foundation for the investment decision. Most companies have their own project delivery system, but almost all of them follow the same underlying philosophy. That philosophy is called front-end loading, or FEL. The idea is straightforward. Project definition should increase progressively while uncertainty decreases progressively. The project moves through a series of phases, starting with business framing, then concept selection, concept definition, detailed definition, execution, and finally startup. At the end of each phase sits a decision gate. A gate is a formal checkpoint where management reviews the work completed and determines whether the project is ready to move forward. Notice that the objective is not to complete documentation for its own sake. The objective is to improve decision quality. As uncertainty decreases, larger amounts of capital can be committed with greater confidence. The terminology may differ between Shell, Chevron, Petronas, or other operators, but they are all applying the same principle. Do not commit major capital until uncertainty has been reduced to an acceptable level. Let's now examine what each gate is actually verifying. The opportunity gate determines whether the discovery fits the company's strategic and commercial objectives and whether appraisal spending is justified. The concept select gate confirms that alternative development concepts have been evaluated and that a preferred option has been chosen. The scope definition gate confirms that the selected concept has been sufficiently matured and that the project scope and cost estimate can be relied upon. The final investment decision, or FID, is the point where capital is formally committed and execution can begin. The startup gate confirms that facilities and wells are ready for safe production. Finally, the closeout gate ensures a successful handover to operations and captures lessons learned for future projects. A very important distinction must be made here. A gate is not simply a milestone. A milestone marks progress. A gate requires a decision. The outcome may be approval, a request for additional work, or even cancellation. The ability to stop a project before additional capital is committed is one of the key strengths of the stage gate system. An FDP is fundamentally a multidisciplinary effort. No single discipline can develop a field successfully on its own. The subsurface team defines the recoverable resources and predicts how the reservoir is expected to perform. The wells team determines how the reservoir will be accessed through drilling and completion strategies. The facilities team designs the systems required to gather, process, and export hydrocarbons. The economics and commercial team evaluates value, fiscal terms, and commercial viability. The HSE and regulatory team ensures compliance with safety, environmental, and permitting requirements. Finally, project management integrates all these contributions into a single schedule, cost estimate, and execution plan. The key message is that the FDP belongs to everyone. Success depends less on the strength of individual disciplines and more on how effectively those disciplines are integrated into one coherent development strategy. Although the FDP framework is the same, its application differs significantly between onshore and offshore developments. Let's start with onshore. Onshore developments generally benefit from lower well costs, shorter development cycles, and facilities that can often be expanded over time. Because of this flexibility, operators can adopt a phased approach and make adjustments as new information becomes available. Offshore developments present a very different reality. Platforms, FPSOs, subsea systems, and pipelines require significant upfront investment and often involve long lead times. Once this infrastructure has been installed, modifications become difficult and expensive. As a result, offshore projects place much greater emphasis on getting the development concept right before sanction. This distinction is important because it influences almost every planning decision made during the FDP process. Onshore development tends to be more forgiving. Offshore development tends to be far less forgiving. Field development planning is practiced in many different operating environments around the world. In mature basins such as the North Sea, development often focuses on tiebacks and maximizing the use of existing infrastructure. In deep-water provinces such as Brazil, West Africa, Guyana, and the Gulf of Mexico, projects are typically centered around subsea systems and floating production facilities. In unconventional basins such as the Permian or Vaca Muerta, development often follows a manufacturing-style approach with large numbers of wells and short development cycles. In Southeast Asia, many developments involve shallow water platforms and clusters of smaller fields. Meanwhile, giant onshore fields in the Middle East and Central Asia require large-scale facilities and extensive well networks. Despite these differences, the planning process remains remarkably consistent. The engineering solutions change. The operating environment changes. But the logic of identifying opportunities, selecting concepts, reducing uncertainty, and making investment decisions remains the same. That is why understanding the FDP framework is valuable regardless of where you work in the industry. One characteristic shared by every field development project is uncertainty. At the beginning of a project, we do not know reservoir volumes with complete certainty. We do not know future production rates with complete certainty. We do not know costs or schedules with complete certainty. As a result, good FDPs are built around ranges rather than single numbers. The industry standard for expressing subsurface uncertainty is the P90, P50, and P10 framework. P90 represents a conservative estimate, meaning there is a high probability that actual outcomes will exceed that value. P50 represents the median or best estimate. P10 represents an optimistic estimate, where there is a lower probability of achieving a better outcome. As projects mature, additional information becomes available through appraisal wells, seismic interpretation, reservoir studies, and pilot production programs. The objective is to progressively reduce uncertainty and narrow the range between outcomes. A common mistake in project planning is optimism bias. Teams sometimes build plans around the P10 case or unconsciously treat optimistic outcomes as the most likely outcomes. Strong field development planning does the opposite. It recognizes uncertainty explicitly and carries that uncertainty through the decision-making process. The key takeaway is simple: uncertainty should never be hidden. It should be quantified, communicated, and progressively reduced as the project moves through each stage gate. When a project reaches the point of requesting investment approval, technical excellence alone is not enough. A sanction-ready business case consists of 4 equally important elements. The first is the technical case. This includes the subsurface understanding, well designs, facilities concept, and supporting engineering work. The second is the commercial case. Even a technically successful project must demonstrate economic viability, appropriate fiscal terms, contracting strategies, and a viable route to market. The third is the HSC and social case. The project must demonstrate that safety risks have been addressed, environmental impacts have been assessed, and stakeholder expectations have been considered. The fourth is the execution case. Management needs confidence that the project can actually be delivered. This includes schedules, cost estimates, contracting approaches, and organizational readiness. Think of these 4 areas as 4 legs of a table. If one leg is weak, the entire business case becomes unstable. That is why investment decisions are based on a balanced assessment of technical, commercial, HSC, and execution readiness rather than technical performance alone. This slide highlights several recurring patterns observed across the industry. The first is premature concept selection. Teams sometimes commit to a development concept before subsurface uncertainty has been sufficiently understood. When new information emerges later, expensive redesigns become necessary. The second is scope creep during define. After the project scope has been established, additional wells, facilities, or requirements are introduced. This often creates cost growth and schedule delays. A third common issue is poor interface management. For example, assumptions made by the reservoir team may not align with assumptions used by the facilities team. Similar challenges occur between subsea and topside systems. Another recurring issue is optimism bias in cost and schedule forecasting. This becomes particularly significant in unfamiliar operating environments or when using new technology. Finally, stakeholder and regulatory planning is sometimes treated as a late-stage activity rather than a core front-end planning workstream. Delays in approvals, permits, land access, or stakeholder alignment can significantly affect project schedules. An important observation is that these issues appear repeatedly across companies, regions, and project types. The purpose of the stage gate process is not simply to organize a project. It is to identify and address these risks before major capital commitments are made. These 3 graphics illustrate some of the most important concepts in field development planning. The first figure shows the relationship between front-end planning and value creation. The greatest opportunity to influence project value occurs early in the lifecycle. Decisions made during concept selection and project definition have far greater impact than decisions made during construction. The second figure illustrates the concept screening funnel. Projects typically begin with multiple alternatives. As technical studies, economic evaluations, and risk assessments are completed, the number of options narrows until a preferred concept emerges. This is a deliberate process. The goal is not to find a concept quickly. The goal is to identify the best concept through systematic screening. The third figure demonstrates the relationship between capital committed and capital spent. A significant proportion of project value becomes committed long before the corresponding money is actually spent. In practical terms, major decisions about facilities, wells, and development strategy often determine future expenditures years before those expenditures occur. Taken together, these graphics reinforce a central principle of FDP. The ability to influence outcomes decreases as the project advances, which is why front-end loading is so important. This case study compares two important offshore development environments. Deepwater developments in regions such as the Gulf of Mexico demonstrate what happens when concept uncertainty remains high at the point of sanction. When major changes are required after approval, such as resizing facilities, modifying development strategies, or changing infrastructure configurations, the consequences can be severe. Additional costs and schedule delays can be significant because offshore systems are expensive and highly integrated. On the other hand, many mature North Sea developments illustrate the benefits of infrastructure-led development. Existing facilities, known reservoir behavior, and established export routes allow relatively simple tieback developments to be executed with lower risk and shorter front-end cycles. The broader lesson extends beyond these two regions. The cost of making a mistake is directly related to how difficult and expensive it is to change the selected concept. This is why offshore projects typically invest more effort in select and define than comparable onshore projects. The less flexibility a project has after sanction, the more important concept maturity becomes before sanction. Let's summarize the key messages from this module. First, a field development plan integrates subsurface, wells, facilities, economics, and HSE into a single development strategy. Second, stage-gated front-end loading is the industry's primary framework for managing uncertainty and guiding investment decisions. Third, front-end planning represents a relatively small share of project expenditure but has a disproportionate influence on project performance and value. Fourth, onshore and offshore developments use the same planning framework, but offshore developments generally require greater concept certainty because changes after sanction are much more costly. Finally, all project inputs contain uncertainty and should be considered as ranges rather than fixed numbers. These concepts provide the foundation for everything that follows in the remainder of the course. Every future module will build upon the framework introduced here. In this module, we focused on the overall framework of field development planning and the decision-making process used to guide projects from discovery to production. The next module shifts our attention to the subsurface. We will examine how geoscience and engineering data are transformed into static and dynamic reservoir models, how uncertainties are quantified, and how reserves and resources are estimated. Since every development concept ultimately depends on the quality of the subsurface understanding, Module 2 begins at the foundation of every FDP, the reservoir itself.